3.7 day 2, we're going to continue looking at our sinusoidal function context and data modeling. Today we're going to dive into our contextual situations. We're going to be looking at contextual situations today and tomorrow. And this is something that's actually pretty heavy on both our unit exam, which we'll have next week, as well as the AP exam. On the AP exam, there are 4 FRQs, and one entire FRQ is dedicated to this. And so it is something that is pretty important in what we are going to be looking at this year. So we're going to be using concepts from the last few lessons in finding sinusoidal functions and equations, and we're going to use those and different characteristics of our sinusoidal functions in our context that we have. We're going to be interpreting real-world phenomena. Very often, and most often, sinusoidal models come from circular motion, which hopefully makes sense because we deal with circles all the time when we deal with sine and cosine functions. We have our sine and cosine and tangent that come from our unit circle. It's a circle. We have our circular functions, equations. We have our sine and cosine and tangent right triangle trig that can be put into circles. All our angles are dealt with circles. So a lot of it deals with sine, with that circular motion. However, that's not the only type of context we could have. We could also have contexts where things are just bouncing back and forth between kind of a maximum and a minimum. And if we think about sine and cosine functions like we see here, that's all that sine and cosine functions do, is that they're that wave that bounces back and forth between a high and a low point, and just keeps on going back and forth, back and forth. So if we can ever talk about a motion that does that, bouncing back and forth between two values, that would be a sine or cosine situation. But again, like I said, most of them are circular motion. So I want us to kind of brainstorm that. What are things in real life that have circular motion? Tires, okay, so if we think the tires on a car, or bike, or any vehicle, those have circular motion. What else? What other things have circular motion? A what? A rolling coin. Yeah, you could talk about a rolling coin, a coin rolling down or rolling across the table. Okay, what? What do you mean a spiral? Okay, so we have like kind of like a spiral diagram that's just going around in a circle. Okay, what else? Like real life situations. Have a tire. Engine, there's parts of the engine that goes in circles. What? A fan, right? We could have the blades of a fan. Fans go in circles. Clock. I have my clock up there that most of us can't read. But it has the hands of the clock, right? This clock's hands of the clock go in circles, circular motion. Okay? So there are lots of things that go in circular motion, and all of them deal with circles. Okay? Which again, if we think about circles, we can have a point on a circle and we can rotate around and come back to that same point. Think about the minute hand and the hour hand of a clock. They rotate around the clock, but eventually go back to 12. Rotate around again and go back to 12. We can talk about that rotation around. Again, going back and forth between 2 or more points. So, the one we have here is a paddle wheel on a riverboat. Can we visualize that, guys? A riverboat with a paddle wheel. Maybe this will help. How many of us have been to Disneyland and have gone on the white riverboat, the Mark Twain? That's a riverboat. It looks like, oh, I don't have it there. All right, there it is. There's my paddle riverboat. Okay. So these are steamboats that for a long time went up and down like the Missouri River and the Mississippi River. The one again at Disneyland is called the Mark Twain because Mark Twain was the author that dealt a lot with the Mississippi River and river boats right there. But we have these paddle wheels that we see right here, those paddle wheels. What shape are those paddle wheels? Circular. In this problem, we are going to be talking about one paddle. So let's say like that one. I don't know if we can see my highlighting there. Let's say that paddle. What happens with that paddle? What's going to happen with this paddle that I have right here? It's going to go around in the circle, right? Why does it need to do that? Because as it goes down, it's going to hit this water and push the water that way, which propels the boat forward, right? But we have that circular motion. So we are talking about the paddle wheel on a riverboat as it moves through the water. So up top here, let's draw a little paddle wheel. So it's a circle, right? Where we have the different paddles going along the circle. And we have that it goes through the water. So how much of the wheel is in the water? Looking at this, how much of the wheel is in the water? Very little bit, just kind of down at the bottom, right? It's not even half. Maybe a quarter, maybe a third. Okay, so not a lot. So we are going to, my thing will move where I want it to go. We're going to kind of put the water down here. There's my water. Okay, and we're talking about, we are saying the vertical distance between the paddle, see, between a particular paddle and the surface of the water. So it's the vertical distance. So like if I picked this paddle up here, my vertical distance would be this. That's the vertical distance. So kind of like the height to the water, from the water, right? What happens as that paddle travels around the circle? What happens to that height? It decreases, right? Like if I'm here, that height has decreased. What keeps happening as it travels around? What happens when it gets to here? The surface of the water. What's my height? 0, right? But that height kept on decreasing until it reached 0, the surface of the water. But then what happens after it hits the surface of the water? Wouldn't that make sense for that height to be negative, guys? Because we are below the surface of the water. But it's only below the surface of the water for a little bit of time, and then what happens? And what happens to my heights as it goes back up? Increases until it reaches that top. What could we say that top is? That max height, right? Max height. But we have that max height. It reaches, but then it goes down until it reaches a minimum height, which is negative, below the surface of the water. But then it goes back up to its max height, and then to the min height, and the max height, the min height. So we keep on bouncing back and forth between this maximum value and this minimum value, and that's what we have in our graph. Okay? So we keep bouncing back and forth. I don't know if it says it in there. Okay, so we have this max here. So what do these points represent, or what does 10 represent in the context of our problem? What is that? The max what? The max height above the water, right? So this would be our max height above water. What would be the x-axis? That's a height of 0. Wouldn't that be the water? Makes sense, right? So we're at our max height, but then our height is decreasing until it hits 0. And if we have a height of 0, that would be the surface of the water. So in these, we have this sinusoidal function, and we want to start applying the context to our problem. Okay. So we have our max height, we have the surface of the water. Question A. It wants us to find the period in seconds. And what does it represent? So let's look at our graph. What is the period of that graph? I agree. If I go from this maximum to my next maximum, that is 10 what? What's my units? Seconds, 10 seconds. So my period, let's go ahead and mark that over here. My period equals 10 seconds. Now, what does this represent in the context of our problem? What is 10 seconds? So if we start at our max, that's how long it takes to go back to the max. I think, what did you call it, Holden? A full rotation, right? It's how long it takes for that paddle to go around that full wheel, to make that full rotation. Okay? That's how long, that's what the period is. In our sinusoidal functions, the period is how long it takes to make one full rotation. Okay? But in this particular case, we can say how long it takes for the paddle to go around the wheel. I'm going to say one time. So that's just one rotation, right? So that is how long it takes. So the period equals 10 seconds is how long it takes for the paddle to go around the wheel one time. One full rotation. So that's my period. Part B says, what is the distance in meters between the center of the paddle wheel and the surface of the water? All right. Where would the center of the wheel be on my graph? Does that make sense? If the center is the middle of the wheel, wouldn't that be the midline of my graph? So it is. Right here. And where is my midline? At 4. Here's my midline. So we mark our midline. And that midline is the center of the wheel. Now that is something that's usually always going to be the case. The midline of your graph should be the center of whatever circular function or motion you're dealing with. So like on a tire, you can visualize the center of the tire. That's where the axle is. We have a tire, right? The center of my clock is where the two hands meet, right there in the center. That would be the center of the circle. And if I was to model that out with the sinusoidal graph, that would be my midline. Okay? So, again, the question, what is the distance in meters between the center of the paddle wheel and the surface of the water? We've marked both of those. What's our distance? What's our distance here? It's 2 marks, but 4 meters, right? So we see that that would be 4. That distance right here is 4. So we have that distance from the center of the wheel to the surface of the water is 4 meters. All right, so we've answered that one, 4 meters. All right, relative to the surface of the water, what is the height of the paddle in meters at t equals 25 seconds? Now I want us to note right here, we are at 20 seconds, so they want us to know where are we going to be at 25 seconds. So, using the periodic nature of this function, what would be the height of the paddle at 25 seconds? I want you to think about it. Talk about it in your group. All right, I think I've heard a lot of you mention it. What would be the height of the paddle relative to the surface of the water? -2. Why? Anybody want to share their reasoning? James says because he says so. Anybody have a better reasoning? Jose? All right, so relative to 10, right, the maximum, 5 steps over would be at, oh, that's only 4. Going over 1, 2, 3, 4, and 5 would be at 15. So 5 spaces over, yeah. Half of our period would be at the minimum, which is -2. So we can use, again, that periodic nature of our function. So that would be -2 meters. Now, I'm going to kind of add in a question here, one that's not in here, but I want us to discuss. So, we've talked about the midline. The midline we saw was the center of the wheel. Talked about the period. That was how long it takes for one full rotation. Let's see. We talked about maximum minimums. What is one characteristic that we haven't talked about yet here? Our amplitude. Let's talk and add that in. What is our amplitude on this function? So I'm going to kind of, right here, amplitude equals 6. What does that represent in the context of the problem? Talk about in your groups. What does this 6? This is 6 meters. What does that represent? Talk about in your groups. Anybody want to share their thoughts? 6 meters. Is Audrey being voluntold? Lauren, since you picked Audrey, why don't you share what you're thinking? The radius? Why? It's half the full thing, full distance. Okay, good. So if we think in terms of a circle, what do we call all the way from one edge to the other edge? Or yes, it's the diameter. If we think about the maximum to the minimum here. I should have made it into arrow. I don't need an arrow. Okay, that is the diameter. What is half of that? Ooh, what is that? I don't know what that is. That is my radius, right? Halfway is the radius. Now, some of you described it using kind of more the terms of the problem. So how do we describe that more in the context of the problem? It is the radius, but how do we describe it? Center of the wheel to the paddle, right? Or to the edge of the wheel, outside of the wheel, right? So any of the paddles. So it's definitely the distance from center to paddle, which, as Lauren said, is the radius. So the center of our circular motion is going to always be our midline. The amplitude of our circular motion is going to be the radius. Okay? Or the radius is the amplitude. Okay? That's going to usually always be the case. All right? Okay. Let's go ahead and move on to this one down here. We have the graph of a sound wave is a sinusoidal function that shows 20 complete cycles between a maximum point at 0.3 and 0.4. What is the frequency? I find kind of doing a quick sketch to kind of get us a little bit better idea of what's going on, a good idea. So we have 0.3, 0.4. Each of those are at a max. Let's see, our max is right here. And so I have a max point here and a max point here. Now normally we would then connect and say, hey, there's my sine function. Looks good. But how many cycles does that represent between 0.3 and 0.4? How many cycles did we get? It says 20. How many did I draw? 1. So instead of 1 cycle, this is saying I'm like doing this. That's not even 20. I don't, we can't draw 20. But from here to here, they're saying there are 20 cycles. What is the length between 0.3 and 0.4? What is that distance? 0.1. So how can I find out? That normally we would say is our period, but it's not, because I'm not doing 1 cycle. If I did just 1 cycle, then I would say, hey, yeah, that's my period. Bam, done. But it's not, because I'm not doing 1 cycle. So how can we figure out our period? Because how do we find frequency? What do we do to the period to find our frequency? We reciprocate it, we flip it, right? So if we know our period, then all we need to do is flip it to get our frequency. So what do we do with that information to find our period? Any thoughts? If I'm doing 20 cycles within that amount of time, is that Audrey? We divide them. What would be that division problem? What divided by what? 0.1 divided by 20. There we go. That's it. Okay? That is your period. They're telling us we have 20 cycles within that. Well, then divide that length by 20 cycles. And that'll give you the length of 1 single period. So then, what is our frequency? What do I do with this? And what is that reciprocal on? Which we can then calculate without a calculator if necessary. 0.1 is 1/10, correct? How do I divide fractions? So what is our frequency? 20 times. We can do that. What's 20 times 10, guys? There we go. There's our frequency, 200, okay? Which I believe would be in seconds, 200 seconds. All right, go ahead and turn the page. Let's talk about simple harmonic motion. All right, so simple harmonic motion. Simple harmonic motion is motion that, for example, can we visualize a grandfather clock, guys? Yes. What is that? What happens at the bottom? What do we call that? The little dangly bit that James is calling it. What is the real name? Pendulum, right? Pendulum. Okay, what does a pendulum do on a grandfather clock? Swings back and forth, back and forth. And didn't I say sinusoidal motion is going between 2 points, back and forth, back and forth? So a pendulum kind of swing, they're trying to hypnotize you or something. That pendulum going back and forth is a sinusoidal simple harmonic motion. Okay, something like a pendulum. Springs are often shown in simple harmonic motion as well. So in simple harmonic motion, notice all we have is A and B. What are the two letters we don't have in these equations? What does C represent? The phase shift or horizontal shift. What is our D? Or the vertical shift, right? So simple harmonic motion has no shifts, just dilations, stretching vertically and horizontally. So just A and B. So if you ever see these words, an object moves in simple harmonic motion, all you need to find is your A and B. So they want us to write an equation. So that is either going to be A cosine BT or A sine BT. But all we need to do is find our A and our B. So what is our A? We read through that problem. What does it say? I have a simple harmonic motion with what? Amplitude of 8. So what is our A then? 8. What else do they tell us? So how can I find my B? If I have my period, what do we do? 2 pi over B equals, what is 0.25 as a fraction? Because we're going to do non-calc here. 1/4. Can I solve for B there? What do? Multiply by B. I have 2 pi equals 1/4 B. So then what does B equal to? 8 pi. We'll actually add one thing in here back to the A, that this is from our amplitude. Okay, so we have A and we have B. However, which one do we want? Sine or cosine? So let's read through the rest of it. They do give us information telling us which one. So let's see, it says at time t equals 0 seconds. So I'm going to go ahead and draw a 0 seconds is right here. Where are we at 0 seconds? What does it say? At t equals 0 seconds, where are we? 0 centimeters. That is our displacement. Our y-axis is our displacement. So we are, and then our x-axis is our time. So we are here. And then what does it say? Moves in a positive direction. So if we don't have a D, that means our midline is the x-axis, and that's going to be the case for simple harmonic motion. Our D is equal to 0. So that means I'm starting on the midline. So which one do we want, sine or cosine, if I'm starting on the midline? So it's sine. However, am I going to be a sine with the positive A or a sine with a negative A? Which one is it? How do we know? Oh, A could be negative. What tells us it's positive, though? There's a piece here. Where does it initially move? It moves this way in a positive direction. So that means I'm going to be going up and then down and around. That is definitely a sine function. So that piece of information tells me we are a sine function. So then I can go ahead and write my equation. See, d of t, I believe, d of t is equal to my A, 8 sine of 8 pi t. And there is my simple harmonic motion equation. So you have to read through. All those little pieces of information are important. They tell us certain things. Okay? So if this one had said that we're starting at t equals 0, we're starting at its maximum displacement, which one would it be, sine or cosine, if we're starting at the maximum displacement? That'd be a cosine, right? And that, or if we're starting at our minimum displacement, that would also be cosine. So you have to pay attention to those words. All right, finding sinusoidal models. So the figure below shows the depth of water along a seawall. The depth is 5 feet below at low tide. So we see our 5 feet right here, 5 feet at low tide, and 11 feet at high tide. So we're talking about the tide. What does tides do? If we go to the beach, what does the water do? Goes higher and lower. Like at some points of the day, it might be very far up on the beach. Other times it's far out, right? But then once it goes to low tide, it comes back to high tide and then to low tide. So it is, again, bouncing back and forth like our pendulum between 2 points. So definitely a sinusoidal model. On any given day, the low tide occurs at 6 a.m. So we see our low tide right here. That is 6 a.m. because this is, let's see. Thought it said it someplace. There it is, T hours after midnight. So this 0 right here is midnight. Okay? So 6 a.m., 6 hours later would be 6 a.m. All right, it wants you to find a sinusoidal model to represent this function. So that's what we're doing yesterday. Find A, B, C, and D, make a sinusoidal model. Notice, does it say anywhere whether it needs to be sine or cosine? Does it tell us it needs to be one or the other? It doesn't, so you pick the one that makes the most sense. All right, go ahead and take a couple minutes, find a sinusoidal function, either sine or cosine, that would represent this function. We have lots of different possible answers. Which one did we pick? What was the one that made most sense, sine or cosine on this one? Why cosine? We're starting at our max. And if we start at our max, then we don't have to do a phase shift, right? Phase shift would be 0. Okay? But do we have to start at the max for our sine or cosine function? No. Right? So I'm going to go ahead and put up, here are the solution that I have. I did the one that you probably did. Okay, we have our midline at 8. Amplitude is 3. Our period was 12, so we solve for our b value by setting it equal to pi over b. And again, if we're starting at our cosine at the maximum, then we don't need a phase shift, and our A is positive because we're starting at the max, not the minimum. Okay? So we have this. Assuming the sinusoidal function, our trend continues, predict the height of the water 30 hours after midnight. So what do I do with 30? Now that I have a function, what do I do with 30? Plug it in, right? So let's do that. We are predicting after 30. However, we're not going to use a calculator, so don't pull those out. So d of 30 equals, I plug it in. That'd be 3 cosine of pi over 6 times 30 plus 8. What is pi over 6 times 30? 30 pi over 6. What does that reduce to? So we have cosine of 5 pi plus 8. All right, what is cosine at 5 pi? We need to find that coterminal angle on our unit circle. Where does 5 pi relate to on the unit circle? So let's think about it. Unit circle time. What angle am I at over there? What radians? Okay? What am I here? 1 pi. What am I here? Can I keep going? What would I be here? Keep going. What would I be here? So then where is 5 pi? What is the coordinate pair at pi on the unit circle? -1, comma. Which one is cosine? That x value or the y value? The x. We need to remember that. Cosine relates to the x value, sine to the y value. So what is cosine at 5 pi? What's the x coordinate at that point on the unit circle? So what is cosine at 5 pi? There we go. So we're able to say that's 3 times -1 plus 8. What does that equal to? 5. And it is in feet, 5 feet. There we go. We're done. Okay. All right. Looking at your graph, where is our tide increasing? When is the tide rising? So when is our function increasing? Where are we increasing, guys? All right, 6 to where? Oh, we see that increasing nature. What is that in terms of time? So I'll say that's 6 a.m. to where? To 12 p.m., which is noon, right? To noon. And where else is it increasing? Where else is it rising? All right, we have 18 hours after midnight to 24 hours after midnight. What would that be in time? 6 p.m. to midnight. All right. 24 hours after midnight would be, well, midnight, right? There we go. Go ahead and turn the page. We have one more problem to look at. We are now going to visit a little spider. It's taking a ride on a fan. All right. We talked about how a fan, or at least it was one that was mentioned, that a fan could be a sinusoidal model because it has that circular motion. So we have our images here. It says a spider rests on the blade of a ceiling fan as shown in the figures. Stopwatch is started, at which point the time is t equals 0 seconds. When t equals 0, the spider is at its maximum distance from the wall, 1.5 feet away. So that is its maximum distance. Hopefully we can see that, because if we're anywhere else, we are at a shorter distance to the wall. So that's definitely the maximum distance, right? Anywhere else would be less than that. Then the spider first reaches its minimum distance, which is 1.5, so there's our minimum distance away from the wall, when t equals 2. That's the first time. When t equals 4 seconds, the spider is back at its maximum distance. So right here, so this means its maximum distance is also t equals 4. The spider continues to move in that circular path. So I see the circular path going this way. That's just how I see it. It could be going the other way. But it's going in that circular path. It just continues to go around and around. Hopefully the fan's not going too fast or to fly off the fan, right? Hit somebody in the head. So we want to graph our function y equals f of t that models the distance between the spider and the wall. So our y-axis is the distance from the wall. So we start at t equals 0. What does it say? Where are we at t equals 0? What is our distance from the wall at t equals 0? at its maximum, which is 1.5. Here is 1.5. There we are at our maximum. What happens at t equals 2? Where are we at t equals 2? It tells us 0.5, which is our, if this is our max, what was 0.5? That was our minimum. Okay, so we're there. And then it told us at t equals 4, where were we again? Back at the max. So we have our sinusoidal function. Can I continue to draw our graph? Let's do so. Where would I be at 6? Where am I going to be at 6? At 6. Should I be back at my minimum? All right. When would I hit my maximum again? At 8. Where would I hit my minimum again? 10. Maximum again? And then it would continue from there, right? So there is our function. Write an equation for f of t. Now that I have a graph, I can pull all my information from it and write an equation. Go ahead and do so. All right, let's go ahead and check our equations. So which one did you guys pick, sine or cosine? Why? Starting at our max, it makes most sense, right? They didn't specify, so I went with cosine as well. I got 1 cosine pi over 2, t plus 0, then plus 1. Does that make sense? Did we get that, guys? All right, one last thing. How would we use our equation to predict where we'll be at t equals 65? We do what? Replace t with 65, right? Yes. Oh, yeah, you're right. I was going by my distance. Good job. So that is, what is my amplitude then? 0.5. Good job. Good job catching that. All right. I was not paying attention to the units of my graph. All right, everybody. Have a good day. You're going to practice some of this on Alex today.